Hi there, welcome to your lesson on the first derivative test. This is part 2, so make sure you watch video 1 before watching this one. Let's get started. So in the last video, we ended with this problem. We had a function, we found the derivative, and we set the derivative equal to 0. That means we were solving for x values when the slope is 0, and we found these two x values. On the graph, we can see at those two x values, negative 1 and 1, we indeed do have a slope of 0. The tangent lines are horizontal. So once we had those, our goal was to figure out when is the graph increasing, which is here, decreasing, and increasing again. And the way to do that was we said, well, if the slope at these 2 points is 0, then the slope before them must be either positive or negative, and that tells us whether it's increasing or decreasing. So for example, we put a x value of negative 2 into the derivative, and we got a positive value. That tells us when we are before the point negative 1 over here, the slope is increasing. It doesn't matter what value we put in there. We could have put negative 2, negative 3, negative 4, negative 5, negative 1 million. It doesn't matter what value, because any value before this point here where there's no slope would produce a positive value and tell us that the graph is increasing there. And then between negative 1 and 1, we chose an x value of 0. We put 0 into the derivative and got a negative value. That tells us that the slope is negative when we have a value between negative 1 and 1. And we can see that on the graph. The slope is negative, the graph is decreasing. And going through that process allowed us to find out when the graph is increasing or decreasing, and it's happening between these points here. All right, so with that in mind, you're going to try one just like that. So make sure you pause if you need to again to see how this process works, and you're going to try it with another function now. So give this a try with this function. Okay, it's a simpler function, but let's do the same process. Find out when it's increasing and decreasing by finding the derivative, finding when the derivative is 0 when there's no slope, and then figuring out what's happening on either side of that place where there's no slope. Let's check our work then. So here's the derivative, 2x. I set the derivative equal to 0, and when you set it equal to 0, you can solve for an x value of 0. So what that tells us is there is a derivative value of 0 or no slope when x equals 0. Okay, great. So what happens on either side of x equals 0? Okay, so I'm going to pick a point to the left of x equals 0, and I'm going to just put negative 1 in there. I could have put any x value which is to the left of 0. I could have put negative 2, negative 3, and so on. What do you get, positive or negative? When you put negative 1 into the derivative, you get a negative value. That tells you before that point the graph has a negative slope, means it's decreasing. All right, what happens when you take a point beyond or to the right of x equals 0? For example, x equals 1. Put that into the derivative, and you get a positive value. That means after x equals 0, the graph is increasing. It has a positive slope. So the function is increasing from 0 to infinity, because at 0, nothing's happening, right? That's when there's no slope. So from 0 to infinity, it's increasing. But from negative infinity to 0, it's decreasing. We got that from here. Now looking at the graph, we can confirm everything. Yep, we can see it's decreasing from negative infinity to 0, and it's increasing from 0 to infinity. We know that our x value of 0, there was no slope, and that's that point right there, the vertex. We see the original as a parabola, so it makes sense that it looks like this, and it's decreasing, then increasing. And this parabola is a positive a value, therefore we know it's concave up. So we could have said in the very beginning, using what we know about parabolas, we didn't have to use this calculus at all. We could have just said, we know it's a parabola, we know it's concave up, we know the vertex looking at this equation is at 0, negative 1, which is right here. So we could have already figured out when it's decreasing and increasing. But here we're just practicing the calculus approach to it, because curves are not always parabolas, they might be more complex. All right, check your work, pause if you need to. Make sure you know how to do this process very confidently. All right, so this brings us to a test called the first derivative test. And in symbols, it looks a little complex, but when we look at it visually, it'll become more clear. So let's take a look at what the first derivative test is, and you should write this down. So if we have a derivative at some point and it equals 0, that means that that is a max or min point, right? So then we continue, because these are called turning points, right? If we have a derivative at some point and it's 0, that means if it's a max or min point, that is a point where the graph is turning. Before that point, it's either increasing and then decreasing after, or vice versa, it's decreasing and then increasing after that point, right? It's either this situation or this situation. So if we have a derivative equal to 0, that means we're here at this min point or we're here at this max point. So before it, it's either decreasing and then increasing, or it's increasing and then decreasing. In other words, that point that we have found is either a max or min. And the first derivative test tells us whether that point is max or min. And here's how it works. So if the derivative is greater than 0 when x is less than c, so for example, if this is your c value where there's no slope right here. So if the derivative when x is less than c, if the derivative, when this here is the derivative is greater than 0, that means positive, and the derivative is negative, less than 0, after the point c, then the function has a local maximum at c. And let me show that on the graph in a second. Let's just write this down now and see if we can decipher it. And the opposite is if the derivative is less than 0, that means negative when x is less than c. And the derivative is greater than 0, that means positive when x is greater than c. Then f has a local minimum at x equals c. And here's what it looks like on the graph. So again, let me put these symbols on the graph and you'll see what this means. So for example, here, the derivative is less than 0 right here, because we can see a negative slope. Okay? Over here, the derivative is greater than 0. So that means this point at x equals c, it must be a minimum point. So that would be like this second statement here. And we can see that here. If the derivative is less than 0, when x values are less than c, so look, derivative is less than 0 when x values are before this point, and when the derivative is greater than 0 right here, positive, when these x values are greater than this c value, then this must be a local min. And the opposite is this. If the derivative is positive, and then the derivative is negative over here, that means this point here, x equals c, must be a maximum point because it was positive and then negative. So it means this must have been a maximum. All right, in the end, this rule is pretty simple rule, pretty simple test. And we're going to use it to test functions. We're going to test what happens before and after a point like this and then answer the question, is it a max or a min? Try this one out. So using the same process, let's find out when this function is increasing and decreasing, and then tell me at those special points if they are max or min points. So let's try the process on your own. Let's see how it goes. It's exactly what we just did with the last problems, but at the end we're going to then determine max or min points as well. Okay, so first we find the derivative like this. Check your work step by step. Then we set the derivative equal to 0 to find out where those max or min points are. When we solve that quadratic, we are going to get two answers, x equals 2, x equals negative 1. So check your work there. So we know, since we began by setting the derivative equal to 0, that at those 2 points, the graph has no slope. So those must be the max or min points. Now we are going to check, oh, I think I have this out of order a little bit. You'll see the graph in a second. Now we're going to check what happens before negative 1. Because negative 1 is our lower x value. So what happens to the left of negative 1? So I put an x value of negative 2 in there. Do you get positive or negative? Okay, so when you put negative 2 into the derivative, you get a positive value. That means before this point, the graph is increasing. So try to imagine that in your mind. It's increasing, and then it gets to this point where there's no slope. So it must mean already that this slope is a maximum point. But let's double check. Let's go after negative 1 and see what happens. So a point after negative 1 is 0. So put 0 into the derivative, and what do you get? Well, you get a negative value. So that confirms that negative 1 must be a max, because we are increasing, we get to negative 1 where there's no slope, and then we are decreasing. Okay, let's check what happens after 2. Okay, so I'm going to go higher than 2, x equals 3. Put that in there. What do you get, positive or negative? And that's positive. So that means after this other point, it must be increasing. So let's see what the graph looks like, because again, the graphs at this early stage, when we're just getting used to this, really help. So we can say increasing, decreasing. We'll take a look on the graph as well. So here's the graph. We can see it's increasing. It gets to no slope point, a maximum point when there's no slope at negative 1, one of those 2 points. And then it decreases and gets to here at 2. and then it increases again. So here's our periods of increase and decrease. All right, increasing from negative infinity to negative 1, and also increasing from 2 to 0, from 2 to 0. And without the graph, we could have said we know these increasing, decreasing intervals because we know what's happening here, right? Before negative 2, it's increasing. Between 2 and negative 1 and 2, it is decreasing. We see that here. And after 2, right here, it is increasing. So make sure you put get these connections together here as you're solving these. And now we have, we can say what the maximum points are also, because by the first derivative test, we know if something is increasing and then decreasing, then that point must be a maximum point. So our maximum point occurs at negative 1, and we got the other value here by putting the negative 1 into the original function, and you get the y value. Same thing with the minimum point. We know this other point must be minimum, because before that the graph is decreasing, we can see that here, and then increasing. So we know that's our minimum point. And again, I put 2 into the original to get this y value. All right, this is kind of tough the first time you're doing this kind of thing. So again, pause this slide and check all the pieces, make sure you understand what's going on. Let's look at one more thing together. So to recap a couple things, a function is increasing when the derivative is positive, and it is decreasing when the derivative is negative, right? Negative slope. Now, there are critical points. Critical points are what we just found. Critical points occur when the derivative is 0. And those are the points we've been looking at. Those points where we reach a max or min point. And we know these are called stationary points. There's no increase, no decrease. It's called a stationary point. But there's also another critical point. Another type of critical point is called, or occurs when our function, the derivative, is undefined. So we're going to look at an example of this right now. I'll show you what this means. All right, we have this graph. So with this one, we'll start with the graph. We can see it. We can see it's a curve like this, like this. It's a rational curve. There's an asymptote here. So there's a break in the function right here at x equals 1, it looks like. Let's check some things out. Let's find the derivative first. For this one, you will need the quotient rule. So try the quotient rule on that. Practice the quotient rule, see what you get. Okay, by quotient rule, we have this, and that simplifies to this. So our derivative is this. So now we're going to follow the same steps. Set the derivative equal to 0 and see what happens, because we want to know when is there a point where we have a max or min point. Okay, so that's one of our critical points. We just said there's these things called critical points, and one of them is when we have a derivative equal to 0. So that's what we've been doing already. Set that equal to 0 and solve. Well, if you multiply both sides by x minus 1 squared, you cancel that, but you end up with a statement that says 0 equals negative 5. That is a false statement. That's not true. That's never true. So we can say there's never a point when there's no slope. There's never a point when the derivative equals 0. This is a false statement, so there's no solution here. There's no answer for x. And we can confirm that on the graph. There's no point when their slope is 0, right? There's no max or min point on this graph. There's always a tangent line that's pointing, like here, there's always a tangent line that's pointing down. And here there's also a tangent line always that's pointing down. There's never a tangent line that's horizontal. And that's what we've confirmed here. So let's look at our other critical point. The other critical point occurs when the derivative is undefined. And the derivative is undefined, well, we know a function that is a fraction is undefined when the denominator is 0. So let's set the denominator equal to 0 and see when that occurs. So set that equals 0. Solve x minus 1 equals 0. That means x equals 1. So we found out when x equals 1, this thing is undefined. And that makes sense because at x equals 1, we have an asymptote. We know there's a break in the graph. So that is what was one of our critical points. So now we're going to take those critical points, which we found out is just x equals 1. And we are going to use that critical point to see what happens to the left and right of it, like we've been doing. So we're going to take a derivative value to the left of that, which means x value of 0, put that in the derivative, and we get a negative value. Okay, now we're going to go to the right of that. So I'm going to take a value to the right of x equals 1, which x equals 2. Put that in the derivative. What do you get? Also a negative. That tells us the slope to the left and to the right of that point is negative in both cases. And that makes sense. So it's never increasing. It's always decreasing, and that makes sense in the graph. Look, this graph is decreasing here and decreasing here. There's never an increase on this graph. There's always a negative slope, negative slope. So it's always decreasing. But we show it in two parts. because there's a gap at x equals 1. And there is no max or min point because we never had a max